This video lesson will discuss the drawing of a neuromuscular junction, and just as a reminder, what we have here depicted is a rough drawing of a synapse. Note that a synapse is when two cells come together for communication, and in this case, in a neuromuscular junction, one cell is a neuron, the other cell is a muscle cell. And in this case, the neuron is called the presynaptic cell, the muscle cell is the postsynaptic cell, and in this cell, we need to get to what is called resting state. Now, some other things that you can see, of course, we have each of these papers that shows how we get to where we are going. Remember that we have to jump across the synaptic cleft to communicate that two cells do not touch each other. If they touched, you probably would get zero communication between those cells. As they butted up, you would have a kind of neurointerference. So what we can see as we're in resting state, one of the things we will notice about our presynaptic cell is it will have secretory vesicles sitting at the terminal end, the terminal neuron, and the terminal neuron is what will communicate with the muscle cell. Inside this terminal neuron are all these little molecules of a neurotransmitter called acetylcholine, ACH, acetylcholine. And acetylcholine is in these secretory vesicles ready and primed to be released when an action potential is needed. Currently, this muscle cell has just finished contraction, and as it's finished contracting, the cell must reset itself. It needs to get back to a normal state. Now, we got to go through how we do that. Now, there's a few things I'm going to draw in on this cell, how we actually get to the resting state. But we also want to note that on the motor end plate of a muscle cell are these little guys that I've drawn in, and these are acetylcholine receptors. So just want to list a little bit of things that I got to talk about before we move on. Now, the cell, when it is ready to get back to resting state, after it's contracted and it needs to reset itself, there is a protein that kicks on called the sodium-potassium pump. Now, the sodium-potassium pump is there to, the sodium-potassium ATPase pump is there to reset the concentration gradient necessary for diffusion to occur of the concentrated ions that we need to discuss. And the sodium-potassium pump will bring in two molecules of potassium cations and kick out three sodium cations. 2 to 3. 2 in, 3 out, and this resets this concentration gradient needed because when the muscle contracts, it was in a process called polarization. Because it brings in less positive in and more positive out, the outside can be said to be positive, and it's going to stay generally positive, and the inside is going to be slightly negative. This is what we call polarized. And when a cell is now polarized, it can be said to be in a resting state, ready to do what the cell needs to be done. So as we think about this guy, it is a high potassium, and it is low potassium on the outside. It also means it is low sodium in, high sodium out. Now this is critical here for the next step that we got to look at as we move on to the next phase that we call depolarization. Now that the cell has been polarized, and we again want to draw in our nice little acetylcholine vesicles that have acetylcholine in them. And we're going to have these guys here. And then we have our acetylcholine receptors, sometimes called nicotinic acetylcholine receptors. And these guys want to bind to acetylcholine. Now, when we actually move to our next state, there's some interesting things that have to happen. One of the first things we have to note here is that this guy when this cell is cocked and ready to go, it now has a high concentration of potassium inside, ready to go. Potassium, very important. Now, what's going to happen since we have reset the concentration gradient? A few things are going to happen in this cell. Number one, the neuron is the boss. And because it is the boss, it will send an action potential down the neuron that will cause calcium influx into the cell. Calcium, I'll draw a darker color here. Calcium, Ca+, will rush in, causing these vesicles containing acetylcholine to bind to the outer end of the terminus of the of your motor neuron, and it will, through exocytosis, send out acetylcholine that will bind to acetylcholine receptors, and once bound, the acetylcholine receptors will result in some drastic changes. Number one thing that will happen once this occurs, you will have sodium channels open. Sodium channels will then open in the cell. Now, by now, the sodium-potassium ATPase pump has cut off. Sodium-potassium pump is closed. Sodium gates open, and Na+ rushes in. Remember, this was a high concentration of sodium cations, low concentration. High to low, sodium rushes in. Once this happens because of the binding, you get a sudden influx of positive ions. So this was positive outside. This now becomes incredibly positive. Once the positive happens, it is now depolarized. A depolarized cell is now a cell that is ready to initiate an action potential. When the action potential kicks in, the cell does some interesting things. And this is when the cell's physiology really goes interestingly. So an action potential will form. The action potential jumps through T-tubules as part of the triads and dumps into the terminal cisternae. So you actually get an action potential running down. It goes in the terminal cisternae, dumping calcium plus ions that are stored in the terminal cisternae out. Once this happens, we already know that calcium, this is sitting just above the sarcomeres. As the calcium leaves the terminal cisternae, calcium outside the terminal cisternae causes a contracting cell. Remember, if calcium is in the terminal cisternae, the cells relax. If calcium is out, it is contracted. Because of the change, calcium will bind to troponin. Troponin will cause the change in conformation of the troponin-tropomyosin complex, exposing G-actin. So G-actin can bind to the myosin heads, causing contraction. And once this happens, the cell has been depolarized. This is a depolarized cell. It is depolarized, depolarizing action potential. Action potential causes release of calcium. You will ultimately get, by the end of this, we find out that the sodium gates will close because of the ultimate change. And when the sodium gates close, you can start, the cell has contracted and it's done. We then have to reset the cell once more. Resetting the cell, remember, requires the sodium-potassium pump. The sodium channels have closed, and we've got to remember kind of what's going on here. Now, we already know two things interesting have already happened to us. We know that the nicotinic acetylcholine receptors have been bound too. Now, we are wanting to close down. And you really can't do this with acetylcholine bound. So one thing has happened, the sodium gates closed, and two things have to happen. Number one, potassium gates open, and potassium now, remember the concentration with potassium. Potassium is low out here, was high in here because of the sodium-potassium pump. So potassium rushes out. Once potassium rushes out, you're now no longer as positive. Now, to further this, the sodium-potassium ATPase pump will kick in, and it will bring in 2 pluses, 2K pluses, because this is going to reset this gradient. We've kicked that out. We want to further we're going to reset the concentration gradient so we can go back to resting. This is going to let some out. It's going to kick out your sodium plus, and it's going to kick out 3 to 2 again. And once this is resetting the cell, and the cell is now back to its area where it can be considered to be negative inside, positive outside, you have an enzyme here that will bind to acetylcholine. This is called acetylcholine esterase. Acetylcholine esterase will bind to acetylcholine. It will then break it down, either recycle it or send acetylcholine back to the terminal neuron. And by the end of this, the neuron will get its acetylcholine back, reset, and be essentially back to where we began at its resting state, ready to go for another contraction cycle as we draw these out. One reason I go through this process with you guys on how to take each from the resting site, how we go from resting to depolarization to repolarization, is so that we may take these individual steps, break them down into individual diagrams so you can learn each one of those. And this ought to help you guys in understanding the processes of forming a muscle contraction, how this associates with the sarcomere. And if you have questions on the sarcomere, please see my lesson on the sarcomere as well. And this concludes my lesson on neuromuscular junctions, and you may find other helpful lessons recorded on integrity for your benefit as well. This concludes my lesson.